Okay, so a couple of quick things about like reviewing velocity versus time graphs first. Okay, so if I have a velocity versus time graph, and it looks like this, what is that object doing? It's accelerating. Okay, its velocity is getting more positive. Okay, it's accelerating in a positive direction. Okay, if I have that same velocity versus time graph and it does this, that object is accelerating and then what? Moving at a constant velocity, right? Okay. Now here's what we have to understand about a velocity versus time graph. Okay, I can calculate the velocity, the acceleration from this graph in the same way I did with the position time graph. Okay, I just have to remember that this formula applies to every graph that has a linear function like this. It would not apply to this one. Okay, but any graph that has a linear function, I can use this equation for. Just the stuff in it is different. Okay, it's still y equals mx plus b, but now y is final velocity, b is initial velocity because it's the y-intercept, how fast you were going at time 0. Okay, m is now acceleration. Okay, it's the rate, m is always the rate at which y changes over x. When it was a position time graph, it was the rate at which we changed our position, meters per second. Now, it's the rate at which we change our velocity, meters per second, or meters per second squared. Okay, does that sort of make sense? Right? On every graph, that slope is going to represent something different. And it's easy to figure out what it represents by simply taking the formula and putting in the units. So if I've got y minus b over x equals m, okay, all I have to do is go, okay, what does m represent here? Y and b are both in meters per second, and x is in seconds. Meters per second is the units for acceleration. Therefore, this represents acceleration. Okay, that's what you want to do. Rather than memorize things, you want to be able to just figure it out each time. That's one skill to learn, as opposed to, by the time you get to Physics 30, like literally 36 different graphs to memorize. Okay? Not to mention all the graphs you would get in chemistry that you would then have to memorize. Okay? You don't want to have to memorize what the slope is on every graph. It's much easier to just have this skill and figure it out for every graph. It doesn't take very long, and you're not going to get it mixed up with anything else. That sort of makes sense? Now, the other thing, and the thing that this graph wants you to do, is calculate the displacement. Okay? So here's what we have to remember about displacement. Displacement is average velocity times time. Okay? That's just v equals d over t, manipulated for d. Everyone all right with that? And I should have the little arrow over this though. Right? So if I'm looking at this graph here, this first one, okay, it starts at what looks to be 0 and ends at some other velocity up here. Okay, so it's changing its velocity between those two numbers. Would its average velocity be halfway between those two numbers? Yes, because if I added those two numbers together and divided by 2, I would get that number, wouldn't I? Yes. Okay. So yesterday, part of the lesson was that if you calculate the area under the line, you're calculating the displacement. On this graph, that area is a triangle. How do you calculate the area of a triangle? Base times height divided by 2. Okay, so if I take the height of this graph and divide it by 2, is that calculating the average velocity? It is. Because we just said, if I took this graph, okay, and I took this value and added them together and divided by 2, I'd get the average. It would be halfway between the two. That's why finding the height over 2 gets you the average velocity. Okay? And if I was going base times height over 2, what's on the base? Seconds, which measures? You're calculating the same thing? Okay? Now again, that's not something I want you to memorize. I don't want you to go, okay, the area under the line on a velocity versus time graph is displacement, and this is then, and the slope for this one is this. Okay? How long did it take me to figure that out?
4 seconds.
Yeah, it doesn't take long. You're better off to have the skill set of look at what's on the graph and figure it out rather than memorize. Especially, like I say, when you get to grade 12 and you're taking physics and chemistry and you're having to memorize God knows how many graphs. Okay, I don't want that for you. You're really likely to get things mixed up that way. Okay, you're way better off to analyze each graph on its own. Okay, so that's what I would do if it was a triangle. What if it was this graph? I have a triangle and a square, a rectangle. Yeah. Okay, can I calculate the area of both of those? Okay, yeah. And for this, what's the average velocity here?
The same as that.
Is it the height of that box?
Yeah.
Yeah, because that's the velocity, right? It just doesn't change. So the average velocity is the height of the box. Is the time still the base of the box?
Yeah.
Okay, still doing average velocity times time. Okay, that's why it works. Now, this question here is ridiculous. Okay, I would never give you a question like that on a unit exam. I give it to you now because it lets you practice. It lets you do the same thing a whole bunch of times and get really good at it. Okay, on an exam, that will tell me whether you know how to do it or not. And only a fraction of the time this question is going to take. All right, so first what I want you to do is draw all the shapes that you're going to have to calculate the areas of, okay, to get the total displacement, okay, because that's what part B, yeah. Okay, then we'll talk about the other ones. Okay, did you guys get into this question at least?
Yeah.
All right. So let's have you draw the shapes. We'll actually do part B first, okay, and then we'll talk about the other parts of that question. Okay, so get all the shapes drawn. Okay, keeping in mind that your triangles do need to be right angle triangles. Okay, so what I'm saying here is I'll give you one. Actually, I'm going to give you two. Okay, that's two separate triangles. All right, so the shapes we've got to draw, we've got those first two triangles there that we figured out, okay? Then we're going to have this triangle right here, and this big rectangle, okay? Now the trick with this triangle is it's only half a second long, okay? Which is also going to put a half in the middle of this one. Okay, that'll be another rectangle, and another triangle there. Okay, so we got a whole bunch of shapes. Okay, in that one, and we have to calculate the areas of, because during those parts of the trip, the object is moving. In some parts of those, in some of them, it's accelerating, and in some it's traveling at a constant velocity. Okay, so in this first triangle here, it's accelerating in a negative direction because its velocity is becoming more and more negative. So I'm going to take the base, which is 3 seconds, and multiply it by the height, -3. So 3 times -3 is 9. Divided by 2 is 4.5. Okay, so during this part, the displacement is -4.5 meters. Okay, it does travel backwards, so its displacement does need to be negative. All right, during this part of the graph, it's accelerating forwards. Which way is it moving? Not moving forwards yet. Okay, from here to here, is its velocity still negative? Yes. Okay, it is possible for something to accelerate in one direction while moving in the opposite direction. Okay, that's how things slow down. Right? If I throw something up in the air, it's moving upwards, but it's accelerating downwards. Okay, so that's totally possible. But that's the kind of question I would ask on a graph, or sorry, on an exam, of a graph on an exam. Okay, because I would say, here in this part of the graph, where does the object change direction? Okay, you would have to say, right here is where it changes direction. Okay, it goes from being negative to being positive. That whole line is accelerating positively, but it's not moving in a positive direction until after 6 seconds. Okay, this little triangle here, sorry for that little aside there, but it was an important one. Okay, this little triangle here has a base of 1 and a height of -3, so -3 times 1 is -3, divided by 2. This little triangle here is -1.5 meters. All right, this little triangle here has a base of 2, or sorry, has a base of 1 and a height of 2. 2 times 1 is 2, divided by 2 is 1 meter. Okay, so positive 1 meter. Then we've got this rectangle here that has a height of 2 and a base of 1, 2, 3, 4, 5. So that's 10. Okay, base times height. Then I got this little triangle that's 1/2 on the base and 2 high. So 2 times 1/2 is 1. Divided by 2 is 1/2. Okay, and then I've got this triangle here that goes all the way down to -6. Okay, so -6 times 1.5 on the base is -9, but it's a triangle. Okay, so I got to divide it by 2, so this is going to be -4.5 meters. Okay, this triangle here goes from -6 to -2, so it has a height of -4, and it has a base of 2. 2 times 4 is 8, divided by 2 is 4. Okay, so that one's -4 meters. This rectangle here has a height of -2 and a base of 1, 2, 3, 4, so that one's going to be -8 meters. And then this little triangle here, height of 2, base of 1, 2 times 1 is 2, divided by 2 is 1, -1 meter. Okay, did that take a long time? Yeah. Okay, like I said, on a test, I wouldn't give you one that made you do the same thing 6 times. Okay, I'd ask you to do a rectangle and a triangle, and probably that would be it. Okay. What do I have to do with all those numbers now? Yeah, do I have to worry about what direction they are? I do, because I'm looking for displacement. Okay, so -5, -4, +4, +4.5, 0, -4, -12, -13 meters. Is that right? No, why did I get -12 on there? Did I miss something? Try that again when it's not in my head. Oh man, how did they do this? Don't know who touched my calculator. I don't like it. It's too big. Anyway, so I gotta move it over here. Maybe that's no, that's not it. Oh no.
Just like try and grab the top left corners.
No, because then it does the whole thing. Yeah, it's a weird, it's a setting, but I don't remember how to get it back to the way I had it. Somebody pushing buttons. Okay, -4.5. Oh, that's why I don't like it this way. -4.5 plus -0.5 plus 1 plus 10 plus 0.5 plus -4.5 plus -4 plus -8 plus -1. I missed something else somewhere.
For the second triangle, it's 1.5.
Oh, there's the 1. Exactly. That's where I missed it. Because I drew right over that line and I didn't see it. Okay, so -12 meters. Okay, everybody all right with that? Okay. Now, let's talk about the other ones here. How would I calculate the acceleration between 12 and 14 seconds? So let's mark the start and end points on our graph here. Here's 12 seconds, and here's 14 seconds. Is it accelerating during that section? Which direction is it accelerating? Backwards. At what time does it change direction from forwards to backwards?
12.5 seconds.
Yep, exactly, 12.5 seconds. Okay, how do I calculate the acceleration? This is tricky because we haven't really talked about it.
Position final minus initial position divided by time.
Close, not position, but velocity, because that's what's on this graph. Then you'll get it. Yeah, absolutely. Okay, so think about this, guys. If I find the slope of a line on this graph. We talked about this a few minutes ago. Okay? If I find the slope of a line on this graph, that's m equals y minus b over x. On the y-axis are the velocities. Final velocity, initial velocity, and time. That's your acceleration formula. It's actually on the back of your periodic table. Okay? That's how we calculate acceleration. Change in velocity divided by change in time. Like we calculate velocity, change in position divided by change in time. Okay? So, all I have to do is plug in my numbers. Right? So for this section from 12 to 14 seconds, my final velocity is -6. My initial velocity is +2. And between 12 and 14 seconds, how many seconds are there? 2. All right, so I've got 8 over -8 over 2 is -4 meters per second squared. Meters per second per second. We just write it as meters per second squared. We talked about that the other day as well. I remember that vaguely in my file. Okay? Remember I said the number's not squared, okay, but the units are. Okay? All right, we did part B. Average velocity over the whole trip. Have I done most of the work for that already?
Yeah.
Okay, how do I calculate average velocity?
Just total displacement divided by total time.
Total displacement divided by total time. Well, we just spent all that time calculating the total displacement, -12 meters, okay? And this whole trip takes
20 seconds.
20 seconds. Okay, so that should give us 0.6, right? Yeah. -0.6 meters per second. Okay. Average acceleration between 14 and 20 seconds. Okay, can I still use this formula? Yeah, because it wants the average. We realize by looking at the graph, there's a section between 14 and 20 where it travels at a constant velocity for a little while. That's okay. They want the average acceleration between those times. Essentially, they're saying, if this line existed, what would its slope be? Okay, that's what we're being asked to find. All right, so all we have to do is go 0 minus -6 divided by 6 seconds. 0 minus -6 is +6. So it would be +1 meter per second squared. It is accelerating positively, right? Like the line is going up. It's not moving forward yet. It's actually slowing down is really what it's doing and coming to a stop. Okay. All right, and then the average speed. Oh boy, I wish I hadn't erased all those numbers. They're still here. Okay, so second entry, and then I'm going to change all these negatives. I'm just going to delete them all. And I'm going to put a 1 on that other number that I missed. Delete. Why am I deleting all the negatives?
Because it doesn't add it.
Right, I just want the scalar number here.
I think.
Oh, it's okay. I didn't miss it.
And turn that.
I'm going to turn it into a 1.
Yeah.
Oh, yeah. Okay, there we go. 35. Okay, so I got 35 meters as my total distance. I got to divide that by
20 seconds.
20 seconds. Pretty sure that's what it's going to come out to.
Yep.
Okay. All right. Those are exactly the kinds of things I would ask you on a test. Okay. I'd give you that little graph. Okay, not one like this. Something like that maybe. Okay. Ask you to calculate total displacement, average velocity, acceleration for the part where it's accelerating. Okay. Average speed or total distance or something like that. Okay. Those are exactly the kinds of things I would ask. Okay. Questions on how that works? Velocity time graphs tend to be the trickier one because we do more with them. Position versus time graphs are pretty straightforward. There's not much other than velocity and displacement to do with those. Okay? All right. Now, if I was to give you this question on a test, just part A, how many marks would it be out of?
I think 1.
Yep. Why would it be only out of only 1 mark?
to draw the shapes. You just have to draw the shapes.
You don't even have to draw the shapes.
It's 0.
Because you're.
Well, okay, it's 0, but why is,
Because of-
exactly. It does the same thing in the negative part of the graph as it does in the positive part of the graph. Okay? If you can recognize that at a glance, which is what a graph is supposed to do for us, that's the kind of question you can answer without having to do a lot of calculating. Right? You just recognize on a graph that, oh, the positive and the negatives are the same. That means they cancel each other out. So the total displacement here would be 0. Okay? All right, try B and C. So you will still have to draw the shapes to do C, obviously.
Do we have to take the curves into account?
No, we're going to assume that those are just nice triangles. There's no curves there. Assume it's just a nice even triangle. Okay? Because we can't calculate that because it's a curve and it's calculus and I'm scared of it. All right, so for this one here, for calculating the acceleration there between 5 and 15 seconds when it's doing the accelerating, okay, A equals VF minus VI over T. So we've got positive 8 minus negative 8, okay, divided by 10 seconds, so 1.6 meters per second squared. Positive acceleration is a vector quantity. All right, and then to calculate the total distance traveled, you really only have to calculate one rectangle and one triangle because they're the same on the other side. Okay, so you'll have 8 times 5 is 40. 8 times 5 over 2 is 20. So 60 times 2 is 120 meters. Okay, and then we got to divide that by the 20 seconds to get 6 meters per second. Okay. Everybody all right with that? Okay. What time is this class supposed to end? 9:20, right? Okay. This one they give us a little bit of extra time. Okay. Ooh, lots of shapes.
It gives it some squares and stuff.
Yeah, this one you can. I put the grid lines on after because it was way too hard to figure out otherwise. Yeah, I think I was. Oh, yeah. Okay. All right, give that one a whirl. Maybe we'll have time to do that before the bell goes. So if I want to calculate the acceleration between A and B, okay, simply using that formula again, VF minus VI over T, so that's going to be 20 minus 0 divided by 2, okay, it's going to give us positive 10 meters per second squared, okay. Now, what if I was to ask you, what is the acceleration between D and E? 0. It's traveling at a constant velocity. Okay, that's another thing I would ask on the test. 1 mark. Okay, you'd be surprised how much work people will show that's all wrong for that. Okay, so just remember, you got to be able to recognize and interpret those kind of things from a graph. Okay, we'll look at the rest of that graph on Monday. Okay, and then we're going to start moving into, we'll probably do a little bit more graphing Monday, maybe Tuesday, and then acceleration Wednesday. We're doing a lab on Thursday. Okay, so that's kind of where we're headed.